You've done this 1,000 times, plugged in your phone charger, left it in the wall, came back hours later, days later, and unplugged it. And if you've ever touched it, really paid attention, you noticed something strange. It's warm, not hot, not burning, just warm. Like it's been working, but it hasn't been working. Has it? Your phone isn't connected, nothing's charging, the charger is just sitting there, plugged into the wall, doing nothing. So why is it warm? What's happening inside that little plastic box when you're not using it? You can't answer that, can you? Neither can most people, because what we call a phone charger is actually a transformer, and transformers have a secret that nobody tells you. They never sleep, they never rest, they run continuously, consuming power, doing work, mechanical work at the molecular level. Every moment they're plugged in. Once you see it, you'll never look at a wall outlet the same way again. Let me show you. The standard explanation is vampire power or phantom load. You might have read about it in an energy-saving article. Unplug your chargers to save electricity. It's not wrong exactly, but it's missing the point entirely, because calling it vampire power is like calling fire the hot bright thing. It's a label. It doesn't tell you what's actually happening. It doesn't tell you why the charger is consuming energy when nothing's connected to it. But once you see what's really happening, once you understand the mechanism, you realize that your charger isn't quietly sipping a little electricity. It's working, physically working, moving, vibrating, fighting against itself. There's something here that nobody talks about when they tell you to unplug your devices. And it connects to the fundamental nature of alternating current, the choice that electrified the world and cursed it with invisible waste at the same time. Let me show you what I mean. Start with something simple, something you can touch right now. Start with something simple. Go find a phone charger right now, any charger. The brick that came with your phone, your laptop adapter, that old charger in the junk drawer. Plug it into the wall. Don't connect your phone. Don't connect anything. Just the charger, plugged into the wall. Wait 30 seconds. Now touch it. Feel that warmth? Not scalding. Just noticeably warmer than room temperature. You felt this before. You probably didn't think much of it. But stop and think about that for a second. That warmth is energy. Heat is the exhaust of work being done. Your car engine gets hot because it's running. Your laptop gets hot because the processor is computing. So what work is your charger doing? Nothing's plugged into it. No electricity is flowing to your phone. The charger is just sitting there, and yet it's warm. It's radiating heat into your room, heat that has to come from somewhere. Here's what's actually happening. Inside that plastic case is a transformer, a coil of copper wire wrapped around an iron core, and the moment you plug it in, that transformer starts oscillating. The AC current from your wall, alternating current, flips direction 60 times per second. In Europe, 50 times per second. Every time it flips, it reverses the magnetic field in that iron core. But that's just the surface, because if that's true, it raises another question. Why would reversing a magnetic field create heat? Here's the first thing you need to understand about magnets. They don't like to change. When you magnetize a piece of iron, when you align all those tiny atomic magnets inside it, the iron resists. It takes energy to flip those atoms, and when you reverse the field, when you try to magnetize it in the opposite direction, the iron resists again. This resistance is called hysteresis. It's magnetic friction. Think about what that means. Your charger's transformer has an iron core. Every time the AC current reverses, 60 times per second in North America, it's forcing that iron to magnetize in the opposite direction, and the iron fights back every single time. That fight costs energy, and that energy doesn't disappear. It becomes heat. Van Beinum measured this in 1890. He plotted the magnetization curve of iron and found that the area inside the loop, the hysteresis loop, represents energy lost as heat every cycle, without exception. Your charger isn't just sitting there. It's magnetizing and demagnetizing its core 60 times per second, losing a tiny amount of energy each time, radiating it as warmth. But wait, that raises another question. If the transformer is already doing this work, why does it get hotter when you actually plug your phone in? Here's where it gets interesting. Most people think the transformer only turns on when you connect a device. That electricity only flows when there's somewhere for it to go. Wrong. The transformer is always operating at full magnetic capacity. The moment you plug it in, the primary coil, the input side, starts drawing current, not because your phone needs it, because the coil itself needs it to create the alternating magnetic field. This is called the magnetizing current. It flows whether or not anything is connected to the output. Here's the thing that should bother you. This current doesn't do any useful work. It's not charging your phone. It's not powering anything. It exists solely to maintain the magnetic field in the core, to keep the transformer ready. And because real transformers aren't perfect, because the iron core has resistance, because the wire has resistance, some of that magnetizing current gets converted to heat. Always, continuously. When you connect your phone, the transformer draws additional current, the load current, to actually transfer power. That's why it gets hotter. But it was already warm, it was already working, it was already wasting energy. Tesla knew this. He designed transformers. He understood that AC's greatest strength, the ability to step voltage up and down with transformers, came with a permanent tax. A transformer must maintain its magnetic field at all times to function. You can't turn it off without unplugging it. Think about what that means. Every wall adapter in your house, every power brick, every device with a transformer, they're all running right now, all of them, drawing magnetizing current, creating heat, wasting power. This is the hidden cost of AC distribution, but that's still not the full story. If this is true, if transformers are constantly doing magnetic work, then why don't we just redesign them? Why don't we eliminate the loss? Now we're getting to the core. Most explanations stop at transformers waste energy, but we're going deeper. The reason you can't eliminate this loss is because of the fundamental physics of magnetic materials. Iron, ferromagnetic materials, have something called magnetic domains, tiny regions where atomic magnets align. When you apply a magnetic field, these domains rotate and grow. When you reverse the field, they rotate back, but they don't return to exactly where they started. They stick, they lag. The technical term is magnetic hysteresis, but what it really means is the past affects the present. The iron remembers which way it was magnetized, and overcoming that memory costs energy. This should break your brain a little. The warmth you feel on your charger isn't just electrical resistance. It's not just inefficiency. It's the physical cost of erasing magnetic memory 60 times per second. You cannot build a transformer without hysteresis loss. Not with iron, not with any magnetic material we know. The better materials, like silicon steel or ferrites, reduce the loss, but they can't eliminate it, because magnetism isn't free. Changing a magnetic field requires work, real thermodynamic work. And here's what nobody tells you. Every transformer connected to the grid is performing this work right now. The chargers, yes, but also the massive transformers on power poles, the substation transformers, the distribution transformers, all of them, humming at 60 hertz, magnetizing and demagnetizing, fighting hysteresis, radiating heat. The entire electrical grid is a network of perpetual motion machines that never stop vibrating. In your normal experience of the world, unplugged devices are off, inactive, dormant. You unplug your phone, close your laptop, and you think, that's not using power anymore. That's at rest. It feels obvious. It feels like basic common sense. Except that's backwards. Your charger isn't off when nothing's plugged into it. Your charger is running. Let me prove it to you. Get a sensitive AC ammeter, the kind that measures milliamps. Plug in a phone charger with nothing connected. Measure the current. You'll see 20 to 50 milliamps flowing continuously into a device that isn't charging anything. That's real current, real power, somewhere between 0.1 and 0.3 watts, depending on the charger. Doesn't sound like much, does it? But think about what this means. First implication, that charger will consume that power every hour, every day, every year. You leave it plugged in. 0.3 watts times 24 hours times 365 days is 2.6 kilowatt hours per year, per charger. Second implication, you don't have one charger. You have 5, 10, 20. Phone chargers, laptop adapters, smart speakers, LED power supplies, USB hubs. Count the wall warts in your house right now. Multiply that vampire power. Now multiply it across every home in your city. Third implication, this isn't a design flaw. This isn't poor engineering. This is the physics of AC transformers. This is what alternating current does. Every transformer on the grid, from your phone charger to the 50-ton monsters at substations, pays this tax perpetually. Every plugged-in transformer in your home is a perpetually vibrating machine, working continuously whether you need it or not. This isn't speculation. This isn't theory. Lawrence Berkeley National Lab measured it. The EPA documented it. Standby power consumption in the United States alone exceeds 100 billion kilowatt hours per year. That's the output of 30 power plants, running 24/7. to keep transformers magnetized, to keep them ready. And once you see this, you realize phone chargers aren't isolated. This connects to everything. Now here's what people miss when they learn just about phone chargers. Transformer losses aren't isolated. They're connected to the entire architecture of electrical power. The same magnetic hysteresis that heats your phone charger also wastes power in every distribution transformer on every power pole in your neighborhood, forces utility companies to generate extra electricity that does nothing but maintain magnetic fields, limits how efficiently we can transmit power across long distances, determines which materials we can use in motors, generators, and inductors, defines the fundamental trade-off between transformer size and efficiency. What looks like many different inefficiencies, vampire power, transmission losses, transformer heating, motor resistance, is actually one thing manifesting in different ways. It's all hysteresis. It's all the cost of forcing magnetic domains to flip direction. The better we make the materials, the lower the loss. Modern amorphous metal transformers lose 70% less than old silicon steel designs. But they still lose something. Because you cannot reorganize atomic magnets without doing work, and you're not separate from this. Inside your body right now, hemoglobin molecules are binding and releasing oxygen, proteins are folding and unfolding, ion channels are opening and closing. Every one of these processes has hysteresis. The configuration your molecules held before affects how easily they change to the next configuration. The same physics that makes your charger warm makes your muscles resist quick movements after sitting still. Molecular memory, state-dependent resistance. That's not complicated engineering trivia. That's beautiful. That's the universe showing you the same pattern at every scale. So when you touch that warm charger next time, remember what you're actually feeling. So why does your phone charger get warm when nothing's plugged in? Because it's not waiting. It's working. The transformer inside is magnetizing and demagnetizing its iron core 60 times per second, fighting magnetic hysteresis, converting that resistance into heat. It's a machine in perpetual motion, doing real thermodynamic work at the molecular level, whether you're charging something or not. That warmth you feel is the exhaust of magnetic friction. It's the cost of keeping the transformer ready to step down voltage the instant you connect your phone. But understanding this isn't just about phone chargers. It's about the choice we made when we electrified the world. In the 1890s, we chose alternating current over direct current. We chose it because transformers made long-distance power transmission possible. We chose it because you could step 100,000 volts down to 120 volts with a simple coil of wire and an iron core. And it worked. It changed everything. It electrified continents. But transformers demand payment. They require magnetizing current. They waste power maintaining fields. They run continuously, invisibly, in every wall of every building, humming at 60 hertz, radiating heat. The fact that we understood this trade-off, the fact that we measured hysteresis losses and built the grid anyway because the benefits outweighed the cost, that's not simple. That's engineering at civilization scale. We don't live in a perfect system. We live in a system that works. And we're still optimizing. Modern chargers use switching power supplies that reduce standby losses by 90%. Smart circuits that power down transformers when not in use. Materials engineered at the atomic level to minimize hysteresis. That's what your warm charger really is. Not a passive device, a magnetic engine that never stops running. Not comfort, not simplicity, truth. If this exploration of transformer physics changed how you see those warm chargers in your walls, subscribe and share it with someone who still thinks unplugged means off. What other everyday devices do you think are secretly doing work right now? Tell me in the comments.